Hello grade 12s, welcome to this video on cell potentials. In this video I'm actually going to go through the examples. But before we get to the examples, just a few things I need to point out. If you end up with a positive value for your cell potential, your overall cell potential, right, it indicates that the reaction will take place spontaneously on its own. It also says that the forward reaction is favored. Excuse me. And it says that the equilibrium lies to the right. Okay, so these are just a few things to notice or to take note of if you get a positive value. Remember that we were making use of the gradients on your table of standard reduction potentials to see if a reaction is spontaneous or not. Here they're saying you can actually make use of a calculation. If your cell potential is positive, it will be spontaneous. To calculate the cell potential, you have a whole lot of options. You can say the cathode half electrode potential minus the anode half electrode potential. You can say reduction minus oxidation, or oxidizing agent minus reducing agent. I like this one and I tend to use this one the most. It makes most sense to me in my brain, right? So if we're looking at the zinc copper half cell, remember in this cell, my zinc forms zinc ions. So it is the substance that is oxidized. And we find that the copper forms copper solid and it is reduced. The copper ions become solid. They gain electrons. So if we want to calculate the cell potential for the zinc copper half cell, galvanic cell, what we're going to do is we're going to take the electrode potential of the copper half cell, which is 0,3 from your table. Then we write minus, because that is what the equation says, what the formula says. And from your table as well, your half cell, your zinc half cell, has the electrode potential of negative 0,76. So we subtract that, and we get 1,1 volts at standard potentials. This tells us that this reaction will happen spontaneously, that the forward reaction is favored. Of course, the reverse reaction is not spontaneous, so it is not favored, and equilibrium lies to the right. So once equilibrium has been established, we're going to have a whole lot of products having been formed. Okay, so let's look at a few examples. Example 5, this is taken from the Olivier textbook. They say calculate the cell potential of the galvanic cell for the following reaction. Copper ions react with iron to form copper solid plus iron 2 plus ions. So we go to our table of standard reduction potentials. We're looking for copper and iron. Make sure that you choose the correct copper and the correct iron. There are two coppers over here. Copper is positive 0,34 and iron is negative 0,44. So now we say, okay, we're going to say E cell according to this. So E cell 0 is equal to E reduction minus E oxidation. Okay, remember, according to this table of standard reduction potentials, the things at the top are the oxidizing agents that are reduced. The things at the bottom are your reducing agents that will be oxidized. So we always take the thing at the top minus this thing at the bottom. And that is going to be 0,34 for copper, since in this case your copper is reduced to copper solid, minus it is minus 0,44 For iron, because iron is oxidized, it goes from being solid to having a positive charge. It loses electrons. And in the end, we end up with a value of 0.78 volts, which indicates to us that this reaction is spontaneous. On to example 7, they say a standard cell potential is positive 0.59. When they say a standard cell, they just mean at standard conditions, temperature, pressure, and concentration. And the reaction for one half reaction of the half reactions is given by this. Calculate the reduction potential of the other cell. So let's just quickly see this substance according to this reaction. Remember, we know that E for the cell is equal to E reduced minus E oxidized. So we need to see if the substance given to us is oxidized or reduced. It goes from a charge of positive 4 to 2 positive, right? So since we go from a more positive to a less positive, it means that electrons were gained. When electrons are gained, it means the substance is reduced. So this substance's value is going to go here at E reduced. So we can start to fill in. We have 0.59 equals. So Sn, we're looking for Sn4 plus. Let's see if we can find it. Here it is. Sn4 plus 2 electrons forms Sn2 plus. And the value we have is positive 0.15. So this equals positive 0.15 minus, and I'm just going to keep it as it is, E oxidized. So solving, we get E oxidized is going to equal to, firstly guys, we move that over. So we get 0.59 minus 0.15. Then we need to get rid of the negative, so we divide both sides by -1. When you put this into your calculator, so that's 0.59 minus 0.15 divided by -1. Oops, sorry, I made a mistake. Please just give me one moment. So we end up with a value here of negative 0.44. So all that we now need to do is go and find out what that cell is. Oh, they don't say so. So we're done with question 7.1. Calculate the reduction potential of the other cell. We've done that. That's given in volts, please. Don't forget that. Then 7.2 says write the equation of the reaction that takes place at the other cell. So remember, the other cell, we have oxidation taking place. Okay, so it's more towards the bottom of the other cell. We look for negative 0.44. Here's our negative 0.44. Oxidation happens in that direction. So we are going to write down for question 7.2. We have iron. So that substance is iron. Iron solid is going to form ions plus 2 electrons. Okay, and that is the other equation. That is example 7. On to example 8. So example 8 says, calculate the cell potential of the following cell notation. So here are the cells, and what needs to happen now is we need to decide what is what. If you remember correctly, I told you we always write down oxidation, then reduction, and we follow that in order to get the cell notation. So that tells me that the substance that is oxidized is on the left, the substance that is reduced is on the right. Okay, so what is happening is silver, Ag solid, is going to lose an electron. Okay, so we say that this substance there is the reducing agent. This is the oxidized species. Okay. Then the reduction half reaction, copper 2 plus, is going to gain 2 electrons in order to form Cu solid. Right? We say this substance is the oxidizing agent and this is the reduced species. Okay, so now they say calculate the cell potential. So E0 cell is equal to E reduced minus E oxidized. Please don't shorten this. Write it down as it is given on your formula sheet, just as I have. So we're looking for silver that loses 1 electron, and we're looking for copper. So here is my copper 2 plus. Nope, incorrect one. Here is the copper 2 plus. And then silver. So let's go and look for silver. Here is silver over here. Okay, so remember we take the reduced substance, that is 0,80, minus the oxidized, that is a positive 0,34. And then we just go and put this into our calculators. So that's 0,8 minus 0.34, and we end up with 0,46 measured in volts. Okay, and that is the end of that example. Now I'm going on to an example from your textbook. It says, so this is the answer series, it says write down the half reactions and the net reaction for the following galvanic cells. If copper 2 and copper half cell is connected to a standard hydrogen electrode, the voltmeter reading is 0,34 volts. They want the half reactions. So, if the reading is 0,34 volts, then guys, this indicates that the Cu is going to be, the copper half cell is the reduction half cell. Now to make things easier so that you didn't have to remember this, we just go to our table of standard reduction potentials and we see where everything is. Here is our standard hydrogen cell. This over here is reacting with the copper half cell, so this copper half cell. Can you see the copper half cell is at the top of the hydrogen half cell? Since it's at the top, it's going to be reduced because increasing oxidizing ability means at the top reduction, at the bottom oxidation. Okay, so that's how you figure it out if you can't remember what the positive and the negative stand for. So write down the half cells. We have oxidation half cells and we have reduction half cells. Our reduction half cell happens in that direction, oxidation in this direction. So oxidation is H2 gas is going to react to form 2H plus 2 electrons. Our reduction half is going to be Cu2 plus 2 electrons is going to form Cu solid. And then they want us to write the net reaction. My electrons are already balanced, so the net reaction is H2 gas plus Cu2 plus aqueous is going to form 2H plus Cu solid. And that is question 1. On to question 2, they say if a zinc half cell is connected to a standard hydrogen electrode, the reading is negative 0,76. Again, I don't remember what the negative means off by heart. I simply go to my table again and then I see where everything else is. Here's hydrogen. My zinc half cell is down there. At the top, since these are galvanic cells, there's reduction, here's oxidation. So going back to the left, we now need to write down an oxidation and a reduction half reaction. Okay. Alright, okay, sorry guys. Over here, reduction takes place in that direction. Oxidation takes place in that direction. So oxidation is going to be zinc solid is going to react to form Zn2 plus 2 electrons. For hydrogen, it's going to be 2H plus 2 electrons is going to form H2 gas. And then the net reaction, we check if the electrons are balanced. Yes, they are. Wonderful. So it's Zns plus 2H plus aqueous is going to form Zn2 plus H2 gas. Okay, and this is an example of a question where you'd have your hydrogen half cell come in. Alright, ladies and gentlemen, we are on the last problem in this video. This is example 9, also from the Olivier textbook. It says, will a spontaneous reaction take place if iron nails are placed in a solution of silver nitrate? There's two ways of checking this. So iron nails, that is my solid, silver nitrate, that is Ag plus ions. Okay, those are the two active materials here. So we're looking for iron and silver in our table. Okay, here is my iron over there. My silver, I think, is towards the top, if I'm not mistaken. Let's try and find it. Yes, here's silver. Okay. There's iron, there's silver. Now, we can do it the way I taught you in terms of the gradient. Iron is going to form the iron ions, and silver is going to form silver solid. Notice, ladies and gentlemen, that we have a positive gradient. You see? Beautiful. We already know that our reaction is going to be spontaneous. But we can also show using this. Right? So that equals reduction minus E oxidation. Okay. So from this, I know that this substance is going to form ions, so therefore it is oxidized. This is going to be reduced. So we take the substance in which reduction takes place, that's that, 0,80. We subtract the substance where oxidation is going to take place, it's that one. And in this case, if I work it out in my head, we get 1,24 volts. And since this is bigger than 0, it's a positive value, we know that this reaction is going to be spontaneous. The answer is yes, it will be spontaneous. Okay, ladies and gentlemen, we have reached the end of this video. There's only one more video on galvanic cells, and then after that we go on to the electrolytic cells. Okay. I hope that you've understood everything. Again, if you have any problems, you guys let me know.